Since we were looking into the t-test, so let's look into what a t-distribution is. So before that we have seen z-distribution or standard normal distribution. This t-distribution is pretty similar to that, except it has more spread, it's more variable, and it is related to another parameter which we will introduce today, that is the degrees of freedom. It was presented by William Sile Guzet, whose technical name which he is adopted in the literature was as student. So rather than calling it as t-distribution, mostly it is famous by the name called as student t-distribution. Here is Guzet. Why he adopted the name of the student, it's an interesting story, since he was working with an industry and he found these issues, some issues with the z distribution. So he wanted to introduce his own distribution, but company never wanted him to publish his work. So he published his work with the name student. So that's why this distribution is called as student distribution. The population is normal, although this assumption can be relaxed if sample size is larger. So that is one of the assumptions. And second assumption for this t-distribution is that the sampling should be at random. There should not be any biasness. Here is how these t-distributions they look like. As I said earlier, these t-distributions they depend upon different degrees of freedom. What is the degrees of freedom? So degrees of freedom is total sample size minus 1. So if your sample is having 10 different experimental units, they can be taken as 10 different independent sources of variation. So we take 10 minus 1. So there is one source of information which we cannot use that. So we have a degrees of freedom is equal to 9. So here we have this t-distribution that is ranging from -4 to +4, just like z, and we observe that at infinity there is a thick green line at the top. So this distribution is kind of similar to our z distribution. We see our distribution with degrees of freedom is equal to 5, which is those yellow dotted lines, and then we have degrees of freedom 2, which are these red dotted lines. As these degrees of freedoms they increase, t become more and more like standard normal or z distribution. So let's look into, for instance, the concept or idea of this degrees of freedom. We'll try to understand with this rugby example. We want to select different players, so we are given a choice to select one of the players. So for example, you pick one of the players. So I give you a choice. Let me pick it for you. So you pick this player 3, then you pick this 8, 4, this one, then you pick this one, this one. So far you are free to pick and you can use your choice here, here, and here 9 of them are taken. There is only one left. Do you have any choice? No. So here comes the concept of degrees of freedom. So if you have 10 sources of these information, you can use 9 them independently or freely. You cannot use the 10th one. You have no choice. So you have 9 degrees of freedom out of total 10 options. So for example, here for any sample where we came up with a sample mean, or for any observation y, for a sample mean we can have y bar. We can calculate t as t is equal to y bar minus mu naught. Mu naught is actually the population mean divided by sy bar, like this equation over here, where this sy bar is standard error of the mean. So it's standard deviation divided by square root of n. So you can come up with any number and you can calculate its t value, and then you can look into whether it is present in the tails or it's not present in the tails. So for example, here we have this degrees of freedom is equal to 10. We draw its t distribution. In the middle, the t is centered around 0. So this t value is 0 over here. And then it keeps on going positive scale towards the right and negative towards the left. Same way, if we take this whole curve whose probability is going from 0 to 1, for minus 1.8 it's present in the lower 5%, so probability is 0.05. In the middle the probability is 0.50 or 50%, and here is the upper 5% of the value where the t should be 1.8 and above. So we have the p is equal to 0.95. up to 1. So here are our top 5% right here, and here are our bottom 5% of the values. Whenever we are doing the hypothesis testing using these t-tests, we need to look into, for that particular degrees of freedom, what is the probability of seeing that event, whether that event is present in these tails, maybe lower 5% or upper 5%. In that case, that event becomes significant. Where we should use t or where we should use z? So if number or the sample size n is less than 30, we should apply t, else we can use z. Since these microarray studies or RNA-seq studies, we cannot afford so many replicates. Our sample size may be 3 or 4 or 5, hardly or rarely it's 30 or above. So most of the time we are throwing these t-tests, we are using these t-distributions. How we do hypothesis testing in using these t-tests? So we can have our null hypothesis that if we are given some mean, we are looking for whether it's equal to this mu naught. So mu naught is, let's assume it's a population mean, and we are coming up with some mean which is not equal to that population mean. So in that case, this is our alternative hypothesis against the null hypothesis. So alternative is mu is not equal to mu naught alternative, whereas this null is mu is equal to mu naught. If it is not equal to mu naught, whether it's present in the two tails, so in that case it's two-tail test. So it should be here if the difference is negative, or it can be here if the difference is positive. So a positive number in the right extreme is a significant number. So anything in this orange shaded area, any number lying here or here, is a significant number. So we need to look into both tails. So in that case, we can call it as a two-tail test. The p-value is the probability of finding this number in these tails is in the shaded area. So here t can be either a positive number or a negative number. We do that in the examples and then it will be more clear to you. Sometimes we are interested, our interest is to find a big number as compared to some given mean, that is mu naught. So in that case our alternative is mu is greater than mu naught. So in that case we are testing it towards this right tail. So that's why we call it as a right tail test. Our alternative is mu is greater than mu naught, whereas our null is mu is less than or equal to mu naught. Now t is again a positive number here. So in left tail t-tests, we are interested in finding some number which is less than mu naught. So for example, our alternative becomes mu is less than mu naught, whereas null becomes mu is greater than or equal to mu naught. So here the p is we see in the shaded area, our t value is actually a negative number. So we are looking into these lower tail. Most of the time we are interested in top or bottom 5%, so that we call it as our alpha. We'll explain that in the next example. So here we are interested in finding this number to be in lower 5%. So t distributions are important distributions where they are like z distributions, and sometimes we are required to compare some numbers with some claims. So in that case we can call them as one sample t-tests.